Hi, I'm Bill Kuszmaul. I'm a new assistant professor in the computer science department at CMU, and I'm a theoretical computer scientist who studies algorithms and data structures. One of the big guiding beliefs in my research is that for many fundamental and basic algorithmic problems, there are often actually still these hidden surprises that are waiting to be discovered. So these are results that overturn a conventional wisdom or that reveal a blind spot in how we think about the problem. And what I've found in my research that often the key to unlocking these hidden surprises is to either use or think about algorithmic randomization in just the right way. So those are two of the big themes in my research, hidden surprises and randomization. And to give a sense of what this can look like, let me tell you the story of kind of one research project that my group did involving a classic data structure known as the linear probing hash table. So this is an old data structure. It was introduced in the early 1950s. It's one that's still widely used today. It's taught, for example, in many introduction to algorithm courses. And although I won't describe the data structure in detail here, it's also a very simple data structure. However, this data structure also very famously suffers from a major drawback, which is a clustering effect. And in order to give you a sense of what that means, let's imagine we fill this hash table up to be pretty full. So a 1 minus 1 over x fraction full for some parameter x. And then suppose we perform one additional insertion into this hash table, and we want to know what's the expected time that that insertion is going to take. Well, it turns out if you're first learning about this data structure, the typical intuition that people have, and in fact, this was actually explicitly conjectured in the late 1950s by early researchers, is that the expected time for the next insertion should be order x. But it turns out this actually isn't what happens. So there's a famous result due to Donald Knuth in 1963, where what he showed is that actually the true expected time for the next insertion is not order x, it's quadratically larger, it's order x squared. And this is because of a clustering effect that Knuth had discovered, which is that the elements in your hash table, it turns out, have this tendency to cluster together into these long contiguous runs that are quadratically larger than you might first hope. So this clustering effect, it's a classic result. It's taught in algorithms and in courses and textbooks. It's something that's actually shaped how people build real-world hash tables. And for about 5 decades, the conventional wisdom was that this is kind of an unavoidable property of linear probing hash tables. A few years ago, one of the research questions that my research group started to ask was, is this clustering effect actually as fundamental as it looks? Or is there some sort of clever way that we could hope to get around it? And what we ended up discovering is that actually, with kind of surprisingly small modification to how this data structure works, you can actually construct a new version of linear probing, what we call a graveyard hash table, that is like linear probing, except that it actually has provably no clustering effect at all. And in fact, the second result that we discovered, one that's actually in some sense more surprising, is that there are even kind of standard versions of the linear probing hash table, versions that were in use even back in the 1960s when Knuth wrote his paper, that already exhibit actually provably less clustering than Knuth's result might have you think. So it's not that Knuth's result is wrong, but actually the clustering that he identified is provably always a temporary effect, but actually dissipates so that the overall effect over time is smaller than this quadratic effect that Knuth had discovered. So this is one example of a result in my research. It's an example of a hidden surprise in a classical problem. And this is something that we have seen again and again in this research area, especially in the field of data structures. It seems that there's lots of opportunities where if you look at a classical problem in just the right way, there's an opportunity to get around kind of these barriers that previously had been viewed as fundamental. So that's a little bit about my research. If you're interested in reaching out, you can reach me at wkuszmaul@cs.cmu.edu. Thank you very much.